Okay, so we're going to look at this problem in our notes. Even this is in the shear flow section. We're not going to do shear flow, so we're kind of E and F I might hit on, but you won't have to worry about E and F. But everything else on here is really good to be able to know. Be able to, hey, what's the maximum bending stress and where is it? Or, hey, what's the bending stress, at this point? Or what's the maximum shear stress? Or what's the shear stress at this point? So we're going to go through A, B, C, D for these types of problems. Then we'll touch on E and F. And before we do that, actually, first of all, this is a very, very long problem. You maybe get some extra sheets of paper. This might be, depending on how large you write, 3-4 pages. I want to draw the shear and moment diagram. I'm probably going to ask for a shear and moment diagram for you, but the shear and moment diagram, those are helpful when you're trying to find the maximum, right? Because that one shows you where is the maximum for the maximum bending stress, the maximum shear. But even, if you want to know the stress at a certain point, well, you need to know the moment at that point, or you need to know the shear force at that point. So then you can just go back to the diagram to calculate the shear, or not to calculate, but the diagram shows the shear force or the moment at that point. All right, so let's draw the shear moment diagrams for this. All right, so we've got a beam. This is kind of a U-beam. Consists of 3 pieces of wood nailed together, and 200 pounds per foot is the magnitude of this distributed load. So if that's 200 pounds per foot, then from statics, let's see, 200 pounds per foot across, 16 feet. So this distributed load, I could replace it with 3,200 pounds. If I sum the moments about A, and sum the forces in Y, but really because it's symmetric, I would get AY is 1,600, BY is 1,600 pounds. All right, so what would that cause the shear diagram to look like? What would that cause the moment diagram to look like? Well, there's no immediate concentrated force, so it doesn't immediately jump up or down, but it does go down by some value linearly, right? It goes down by some value linearly. What value does it go down? Well, that area right there, which is 200 by 4, so it goes down to negative 800, then immediately jumps up by 1,600, so now we're at positive 800. Then it goes down right here. How much does it go down? By this area right here, which is 200 by 8, so it goes down by 1,600, so we're back here at negative 800. It goes up 1,600, back down there. So that is the shear and moment. That's the shear diagram, V. Now the moment diagram. 3 things I'm looking for. I'm looking for a concentrated moment, an applied moment, an external moment, a moment that's drawn on there. There's none in this problem. But then I'm also looking for the area under the curve, and V is the slope of M. So first of all, this area under the curve, that would be a negative area of 1/2 base times height, so 1/2 4 by 800. That would bring me down here to negative 1,600 pound. Let's see, pounds times feet. How would it get there? V is the slope of M. So first I have a slope of 0. And I've got a steep slope of negative 800. So it would be this curvature right there. Then I've got a positive area right here. So that would bring me up by 1600. So it actually goes back to 0. How would it go? V is the slope of M. It would go like this. Then I'd have this negative area. It would go down here. This positive area would bring me back up to 0. This would also be negative 1600. Okay, so step 1. Sometimes I ask for it, sometimes it's just helpful. Draw the shear and moment diagrams for these beams. Alright, then for the shear, we can find shear stress. For the moment, we can find bending stress. So, part A, determine the location and magnitude of the maximum compressive and tensile bending stresses. Alright, so the bending stresses, my over I, right? Bending stress, my over I. So the maximum moment would be 1600, and it'll be negative 1600. We'll talk about that. But what is the Y? What is the I? So first of all, let's do the I. Let me see if I have room on this page. The I, I'm going to use the I for my over I, for VQ over IT. That's just the I of the shape of the cross section. So maybe it'll be given. Some are given. This one's not given. We're going to have to calculate the moment of inertia. And this is the I about the neutral axis. I don't even know where the neutral axis is yet. So first, step 1, let's calculate the centroid. Step 1, let's calculate the centroid. The Y bar, Y tilde A over summation of A. Now, if this was symmetric top to bottom, I wouldn't have to calculate centroid. It would be at the middle. This is not symmetric. So if it's this U-beam, if it's an I-beam, the top is different than the bottom, you might have to calculate the centroid. So here, let me calculate the centroid. All right, it would be, I'm going to break this up into 3 triangles. Measured from the bottom. I'm going to measure these from the bottom. So for this first shape right here, its location of its centroid would be 1.5. Let me see here. Yeah, do this a little differently than what I'm following. So follow it with me here, see if we can get this right. 1.5 would be the Y tilde for that shape. And then its area is 0.5 by 3. And that's exactly the same as this other shape. So let me go ahead and do that one and multiply it times 2. And then the top one, its location of its centroid would be 3.5. And its area, 1 by 3. All right, so that's the Y tilde times the area of one, the Y tilde times the area of the other one, and then the third one, I just multiplied this one by 2 because it's the same. Then the total area would be base times height, and there are 2 of those, plus base times height of the top. Total area. All right. So the location of the centroid is 2.5. It comes out to around nice, even 2.5. And I'm measuring from the bottom, inches from the bottom. All right, so that is where my neutral axis is. My neutral axis is right here, 2.5 from the bottom. I need to know that for a number of different reasons. Got to know where the neutral axis is. Now, for the moment of inertia. I think I'll keep with those same three shapes, same 3 rectangles. Just sum up each one's I plus AD squared. Sum up each one's I plus AD squared. All right, so the I for that rectangle would be 1/12 B, sorry, 0.5, 1/12 B H cubed. But that would be about that point right there that is the middle of that rectangle. That's at 1.5 from the bottom. I need to move it to 2.5 from the bottom, so I need to move it I need to move it 1 squared. And I need to do the exact same thing for the other rectangle over here. All right, and then the top one, 1/12 B H cubed, but that would be about that middle of that shape. I need to move it down. I think I need to move it down 1 as well. So it's area 3 by 1, move it down 1 squared. All right, so I've got the I for this shape to be 8.5 inches, inches to the fourth. 8.5 inches to the fourth. Let me kind of box it. Didn't ask for those, but I'm going to use those again and again. So let me box those in. Okay, now I think I'm ready. Determine the location and magnitude of the maximum bending stress. Alright, but it wants the maximum compressive stress and the maximum tensile stress. Alright, you can tell, you know, the top half, let's talk about this for a second. For a negative moment, that kind of makes my pool noodle or my beam, makes my beam kind of frown. All right, for a negative moment, do you see why there would be tension on the top, there would be compression on the bottom? You can think about where we started this chapter with those lines, those 3 lines. If I had a 4-inch line here, a 4-inch line here, a 4-inch line here, this green 4-inch line on the bottom would get compressed to maybe 3 inches, you know? Or imagine putting your finger right here. It would get pinched, right? It would get compressed. So a negative moment is like a frown. And with that one, there would be tension on the bottom, compression on the top. So what it's really asking is, hey, calculate the, compression on the bottom, tension on the top. So here it's saying calculate the maximum compressive stress on the bottom at this maximum moment of 1600, and calculate the maximum tension at the top at that maximum of 1600. All right, let's see if we can do that. So the bending stress, let's do at the very top at a moment of negative 1600 at that location right here, at this location right here, because I know from the moment diagram that that's the maximum magnitude that we will get for the moment, maximum magnitude of 1600. So let me do the my over I right here. So the moment, 1600 pound-feet. The y value. All right, so at the very top, my y value, y is measured from the neutral axis. The very top, that y value is going to be 1.5. Y is just how far you get to the point you're interested in. If I'm interested in the point, if I'm interested at the top, then my y value 1.5 inches. I don't think units are going to work out here. Divided by I, 8.5 inches to the fourth. So I think I want to get rid of that feet, change it to inches. So multiply it times 12. And so now I've got PSI. PSI would be my units. All right, 3388 psi. All right, is this tension or compression? The way that I do this, I would give it tension or compression myself, depending on positive or negative moment. This is a negative moment. Negative moment is a frown. A negative moment at the upper half of the negative moment, the bending stress would be tension. This would be in tension. Tension. So that is the maximum tensile bending stress. Okay, now the book would have you put some positives and negatives in here. In the book, its equation for bending stress is negative my over I. So if we had negative my over I right here, but then we also had a negative moment. This is positive 1.5 because we're going above the neutral axis. Then you see how this would come out positive, and positive is tension, like we had done. So the book would have you do negative my over I, and be very careful with the sign for your moment and the sign for your y. But we'd both get tension if we're looking at the top. All right, let's look at the bottom. At this location, my over I, 1,600 pound-feet. Now this is not symmetric. The y to get to the very top is different from the y to get to the very bottom. The y to get to the very bottom would be 2.5 inches. Multiply it times 12 for your conversion factor. I is the same. I is just for the shape, so it doesn't matter where you're looking at. This would be 5647 psi. And so knowing that it's a frown, knowing that it's in compression, knowing that it's a negative moment, tells me it's a frown. And underneath, on the bottom of the frown, right, this would be in compression. So let's put negative 5647. So that's the maximum compressive bending stress. Maximum compressive bending stress. This is what the book would have you do. The book says the equation for it is negative my over I. So we've got a negative here. The moment is negative, but the y is below the neutral axis, so we would put a negative there. So do you see we would all come out with a negative answer for compression. Negative answer for compression. Okay. All right. That was just part A. Let us keep going. All right, so now it doesn't say the maximum. It says, hey, calculate the bending stress at this location. So at the interface between the boards, so we're talking about right here, the interface between the boards, and 2 feet to the left of point A. So it's telling me to look right here, 2 feet to the left of point A, and look right here at the interface between the boards. All right. Well, let's see here. I know that this would be my over I. So what is the m at this location? Well, it'd be that value right there. Well, what's that value right there? Well, it would be that area of that triangle right there. What would the area of that triangle be? 1/2 base of 2, a height of, if we're halfway here, this is linear, a height of 400. So this would be 400 pound-feet. Negative 400 pound-feet. And does that make sense? The curvature of this kind of helps you. Yeah, that makes sense. This is an x squared chart. So yeah, negative 400. So I like to not put the negative and just visualize it myself, whether it's compression or tension. The y. All right, so if we're looking, it wants us to look at the interface between the two boards. So right here, where they're coming together, if I know my neutral axis is at 2.5 from the bottom, and that interface between the boards is at 3 from the bottom, then my y is 0.5 inches. Multiply it times 12, that's conversion factor, 8.5 right there. So this would be 282 psi. Is that compression or tension? The way that I do it, I know it's negative, so my pool noodle is bending down this way. The location is above the neutral axis, and so this would be tension. The book would tell you the equation is negative my over I, so I've got a negative due to the equation, and then I've got a negative 400. Comes out positive. All right. All right, so now we're going to start talking about shear stress, maximum transverse shear stress. So determine the location and magnitude of the maximum transverse shear stress. All right, so where is the maximum transverse shear stress? It would be right here at any of those locations, and the maximum magnitude would be 800. All right, where on our cross section do we see the maximum shear stress? We see it at the neutral axis. We see the maximum shear stress at the neutral axis, right here. All right, and so let me see here. Okay, sorry. Yeah, so we need tau is VQ over IT at this location. So we know that V is 800 pounds. That's the shear force. All right, the Q is going to be the hard part. We know the I is going to be 8.5 inches to the fourth. What is the thickness at this location? So this is at the neutral axis, where we have a shear of 800 pounds. The thickness right here. All right, well, let me think about my Q, y bar prime, a prime. I'm going to look at the top of this. You could look at the bottom. So I'm going to look at that. So anyway, my thickness, I would need to include both of these thicknesses, 0.5 and 0.5. So I need to have a thickness of 1 inch right here. All right, so Q, here's the hard part, Q. Q is y bar prime, a prime. A prime wouldn't be too terrible to find for this blue shape that I just penciled in. But the y bar prime, where is the centroid of this? That would be tough to find the centroid of this. So I'm going to say Q is the summation of y bar prime, a prime. So I'm going to break this up into 3 rectangles and 3 shapes. And I'm going to do the y bar prime for one times its a prime plus the y bar prime for another times its a prime plus y bar prime for another times its a prime. So let's start with these small ones. The small ones, the area is 0.5 by 0.5. And the y bar is to the location, the distance from the neutral axis to the centroid of a prime. So that would be 0.25. So this would be 0.5 by 0.5 by 0.25. Sorry, this is the a prime right here. This is the y bar prime right here. 0.5 by 0.5, and then the y bar prime is 0.25. And do you see that the other rectangle on the other side would be exactly the same? All right, so that's the y bar prime, a prime for those rectangles. Now the y bar prime, a prime for this rectangle right here, it's a 3 by 1. Let me go ahead and do that. It's a 3 by 1, and then the y bar prime is the distance from the neutral axis to the centroid of that that would be 0.5 just to get to the shape, another 0.5 to get to the middle of the shape. That would be 1. Would be its y bar prime. And so there is my Q. That was a tough Q, right? But there's my Q. All right, so I've got a tau of 94.1 psi. A tau of 94.1. Sorry, no. I'm jumping ahead. Let's do the math here. A tau of 294 psi. 294 psi. So that was the maximum. So I needed to look at the shear moment diagram to figure out, hey, what's the maximum absolute value? And then I need to know, hey, the maximum occurs at the neutral axis. So I'm looking at the neutral axis right here or here. And it is changing immediately to the left of A. It's in the negative direction. Immediately to the right of A, it's in the positive direction, but the magnitude is going to be 800. All right, so 294 is the maximum. All right, but what if it wanted to know the VQ over IT? So the next part D, what is the VQ over IT? 1 inch from the bottom and 2 feet to the left of A. So I need to cut it right here. So I need to use this value for V, 400, right? If it goes linearly from 0 to 800, and right in the middle it'd be 400. So at this cut, I know it's 400. And 1 inch from the bottom, so I need to cut it 1 inch from the bottom. Right here. Cut it 1 inch from the bottom. All right, so what would be VQ over IT right there? It'd be 400 pounds. The Q, we mentioned this earlier. Q is y bar prime A prime. And the area, do I want to do both of these legs or just one of these legs? You can do either of them. I think I'm just going to do one of them. The area is going to be 0.5 by 1. The area is 0.5 by 1. And the y bar prime, all right, let's think about this. If my neutral axis is right here, 2.5 from the bottom, I want to know what's happening at 1 inch from the bottom. So I need to go down. I need to go down 1.5 just to get to my point. But y bar prime is not just the distance to your point, it's the distance past your point to the centroid of A prime. So this would be 1.5 plus another 0.5. This would be 2 inches. My 2 inches would be my y bar prime. Here's my A prime right here. Here's my y bar prime. Divided by I, 8.5. And the thickness, since I'm only looking at one of those legs, 0.5. If you wanted to look at both of those legs, this is what would happen. You would have 2 of these y bar prime A primes, but you would also have 2 of these thicknesses. You see how it didn't change my answer? All right, so I've got pounds per inches squared. This is going to be the 94.1 psi. All right, this is the 94.1 psi. Is the shear stress at that location. Shear stress at that location. Okay, let's real briefly talk about, maybe we can fit this. I don't know if I can fit this on this page. We'll see. E and F. All right. Determine the required nail spacing if each nail can support 650 pounds in single shear. So I know that the Q is the force per nail times the spacing of nails per inch. spacing nails per inch. So if I know that this force per nail is 650 pounds, and we want to find the required spacing, of nails per inch. Okay, sorry. Q is F times S if we do force per nail and nails per inch, but Q is F over S if we do force per nail and inches per nail. That's another way of thinking about this and doing this. Shear flow, lowercase q, shear flow. What is shear flow? Shear flow is VQ over I. All right, so real briefly. Shear flow is VQ over I. What's the maximum V I'm ever going to have? 800. What's the maximum... Sorry. Yes, the maximum V I'm ever going to have is 800. What Q do I need to be worried about? I need to be worried that the nails... I need to make sure that the nails can take the shear right here. The nails are nailed in here, right? These nails are nailed in, and they're keeping this together right here, right? They're keeping this together right here. So I need the Q right here at the interface where the boards are being held together. All right, so the Q at that location from the neutral axis would be y bar prime, a prime. The a prime would be 3 by 1. The y bar prime would be 1. It would take me 1 inch to get from the neutral axis to the centroid of a prime. All right, divide that by 8.5 inches to the fourth. All right, so that's VQ over IT. Let's go ahead and get that value, 282 pounds per inch. But this is also, VQ over IT, it's also force per nail divided by inch per nail equals force per nail divided by how many inches per nail. And if I know this is 650 pounds, and that's force per nail, and it's being nailed in 2 places, so I'm going to take this 650 times 2, and the inches per nail, S, is what I'm solving for, and I would get S 4.6 inches per nail. So that's kind of the minimum of 4.6 inches in between each nail so that it can withstand the largest V at the place it needs to hold them together at the interface between the 2 boards. Okay, this part right here is shear flow. You don't have to know. This is just extra. Everything above here, though, you do need to know. But everything below here is just extra. Shear flow is good to kind of get the spacing of the nails to figure out the shear force at the interface where the boards are being nailed together. All right, and we'll do F real quickly one last time. Let's determine the maximum distributed load the beam can support if each nail can support 500 pounds in single shear and the nails are spaced 6 inches apart. All right, so Q is force per nail over inches per nail. If I know that the force per nail is 500 pounds and there are 2 rows of nails and the spacing 6 inches per nail, my shear flow is 166.7 pounds per inch. Shear flow is also equal to VQ over IT. VQ over I. And if I know that the Q at the interface is 131, and I know the I is 8.5. I can get the V, 472 pounds. So what it really told me, by telling me that each nail can support 500 pounds, and the nails are spaced 6 inches apart, I found the shear flow, and from the shear flow, I can find the V. That's the maximum V that those nails can handle. That's the maximum V that those nails can handle. So if that's the maximum V those nails can handle, what is the maximum distributed load? Well, I would just go back and look at my shear diagram. My shear diagram was for a uniform distributed load. This is what my shear diagram looks like. So it's telling me that I can only have 472 right here. Instead of we had 800, I can only get up to 472 right here. So what W would get me up to 472? What distributed load, if this is 4 feet, what distributed load, what height W over 4 feet would equal, that would equal 472. 4 times the height equals 472. This is 4 feet times the height. Let's see if the units work out. This is pounds. This is feet. I would get a W of 118 pounds per foot. 118 pounds per foot. All right. Don't worry too much about those last two parts. Don't worry too much about those last two parts. What I want you to get out of this problem, be able to draw the shear moment diagram, and I could ask you 4 things. I could ask you, say, hey, what's the maximum bending stress? So you need to find the maximum location on your, let's talk bending stress. You need to find the maximum moment on your moment diagram, and you need to know that the maximum bending stress occurs at the very top or the very bottom. So that's one thing I can ask you. I can ask you part A, hey, what's the maximum bending stress? But I could also ask you, hey, what is the bending stress at this location at this point, right? I can ask you, what's the bending stress at this location at this point? Same thing with C. I want you to be able to find the maximum shear stress. So you need to look at your shear diagram. Where's the maximum magnitude of shear? Where's the maximum shear occur? At the neutral axis. But I could also ask you, hey, what's the shear stress at this location at this point? All right, E and F are just extra for free, okay? So look back at that problem. Make sure you can draw shear moment diagrams. Hey, make sure you can calculate the centroid and the moment of inertia. Make sure you can calculate the centroid and the moment of inertia, especially if something is not symmetric. Makes it a lot harder. All right, and then calculate the maximum bending stress or the bending stress at a location, the maximum shear stress or the shear stress at a location.